So, hello everyone. Welcome to TCU ARC lecture series. I'm Heran Jun, Associate Professor at UC Merced. I'm the moderator of this talk. Today, we are excited to host Dr. Yifan Sun's talk about the beloved GPU simulator MGPUSim. After around 30 to 40 minute talk, we are going to have a 10 to 15 minute Q&A time. Feel free to ask over the live chat. We'll try our best to catch most of the questions if possible. Let me introduce Dr. Sun first. Dr. Yifan Sun is an assistant professor at William and Mary. His research interests lie in GPU architecture, performance evaluation, and performance modeling. He is the initiator and maintainer of multiple open source projects such as MGPUSim, Akita, and HeteroMark. These tools have been widely used by the community to simulate larger-scale parallel processors, especially GPUs. He received NSF Career Award in 2025. Please, Dr. Sun, the stage is all yours now.
Okay, then thank you everyone for watching the live stream. I see there are 7 watching right at this moment, and this is our first time trying live stream. So let's try to see if there's any technical problem, or then if how well this thing works. Then probably later on we can have more live lecture series in the future. So my talk today is empowering computer architects with human-centered features in MGPUSim. This is a not really traditional topic, so I want to start with where the story starts and how we start the whole theories of project. We started by the time when we are working on this paper called Spartan, a sparsity adaptive framework to accelerate the deep neural network training on GPUs. I don't want to talk anything about sparsity at this moment, but that time when we were developing this sparsity adaptive framework, is an architecture design for GPUs, we tested on MGPUSim on a simulator and also tested on a hypothetical NVIDIA GPUs. Then our performance was like 20 times faster than NVIDIA GPUs. We know NVIDIA GPUs was highly optimized. Now at that time we just cannot believe this result. But our result is literally 20 times faster than NVIDIA GPU, and we only really have the GPU execution time, the total execution time, as the data point. So what's the problem? Is there a problem with the simulator, or is it really our simulator that is performing that well? We don't know. So the first order and I was really confused by that time. And I think probably if you are a graduate student or you're a junior professor working in this domain, you probably will have some similar concern that you don't really have a good understanding of your simulator's report, or you cannot really understand why a hardware have a certain behavior. So by that time, we're trying to solve this problem. Then definitely by solving this problem is by doing more experiment. That's the conventional way. But we don't really want to solve this problem as itself. We think this is a meta problem. There's an explainability problem. So we want to solve the meta problem rather than solving the problem itself. So we consider our mission is to develop solutions to help developers to understand and interpret computer architectures better. And here, as you can see, I highlighted developers and computer architects, computer architecture. So on one side, we have developers, which are human. On the other side, we have computer architecture as a technology. Now, when human and technology combines together, we consider this is a human-computer interaction problem. So we say we need human-centered method problem to solve human-centered method to solve this type of problems. So that's how we start this a series of tools that can help developers to understand and interpret computer architecture better. Eventually, we started this new direction called human-centered research in computer architecture domain. So before I introduce something concrete, let me introduce what we have, the starting point. We have Akita and MGPUSim. If you don't know what they are, let me very briefly introduce them so that you can know our background. So we have MGPUSim. MGPUSim is a GPU simulator. So you probably have used something like Gen 5, GPUSim. MGPUSim is not very special It's a GPU simulator that supports OpenCL kernels running on AMD GPUs. Um, it highlights the capability of running multiple GPU, like simulating multi GPU environment. And as I counted recently, there are at least 39 papers used MGPUSim to validate their ideas, not only citations, but they literally use this tool in the evaluation section. So I don't want to talk too much about MGPUSim. I want to talk about human-centered feature. But when we develop MGPUSim, a very interesting direction that we went to is to start this new simulation engine called Akita. Because we have done so many optimizations on the core part of MGPUSim, we think this core part may be shared as a library that can be used by other simulators. Therefore, we started this tool called Akita. It's basically extract the core of MGPUSim so that it can support the development of future simulator. We call it a similar engine. It's just like a game engine so that it can support the development of new simulators. So I want to talk about some unique features about Akita. The first of all, it uses Go program language. Then I know every time I talk about it uses Go program language, there are a lot of controversies on the language selection. But if I talk, as you listen to my talk later today, you may realize, like, if I don't use Go, then how hard all these features can be implemented. Then Akita is a pure event-driven simulation engine. Then it can support programmer transparent parallel simulation. So you don't need to do anything, it's automatically parallel. We have a classic component port and connection definition so that you can define every hardware element as a component. For example, you can define a cache, a core as a component and connect a cache, a core, and a memory unit together using port and connections. It's really flexible. And based on that, we have this automatic sleep and wake up schedule so that we can put some component to sleep so that we don't need to keep ticking this component. So tick here is a specialized event that is scheduled in every cycle. Then Akita framework has this capability of automatically put component to sleep so that we don't need to keep ticking it, but we can still get the correct result as if it's ticking every cycle. Then we also have a rich first-party component libraries. For example, we have write-through caches, write-back caches, DRAM unit that is ported from DRAM 3, and the network on chip models that can be directly used from the Akita framework. So this is Akita framework. And one particular challenge that you can consider that when we extract an engine out of a simulator, we're no longer concerning something concrete, and we lose some context, right? For example, if you are writing in Gen 5, you can pretty much optimize for the CPU model, right? But in Akita, if we consider this a similar engine, we have to assume this is not for CPU, not for GPU, not for some CGRA devices, not for some actuators. Now, any user can use this simulator engine to build anything. Therefore, you can see later on we keep these features, these human-centered features, to be really generic. So generic really, the generality also give us a lot of power and also a lot of challenges in designing these tools. So let me start with the first tool that I want to introduce today. We call it Akita RTM. It's a real-time monitoring tool. RTM stands for real-time monitoring here. Then we call it a during simulation monitoring tool. So what the problem it tries to solve? Consider this scenario. Assuming one day your advisor tell you to run a simulation. And you can run a simulation, then a week later, you get some result. And then, simulation runs really slow. So we really need to run a really long time to get some simulation result. So after a week, you get a lot of result. Then, but you realize there's a problem. So like you misconfigure something. Or you write some program with some bug, although it can get some result, but it's not accurate. It's not what exactly you want. Or it's just a process that you keep trial and error that you want to try different combinations. It will waste a lot of time, right? Then if you realize problem, you may run another simulation. Then a week later, you realize another set of problems, then you start another simulation. Then this whole process is really slowing down our innovation because it increases our turnaround time. Every time you start a simulation, then you need to take a very long time to get a result. Then your result may be wrong. So then we start this real-time monitoring tool. Um, it's very different from the existing approach. The existing approach mainly focus on how we can accelerate simulations that we assume that simulations can run without any problem, that can get a result. We want to run it, finish it as soon as possible. But the solution of Akita RTM is to terminate problematic simulations with the help of the programmers. So we consider the programmers are human, the developers or computer architects are human. Now we use their power to help us to terminate the problematic simulations as soon as possible. Probably in 5 to 10 minute simulation, you can monitor what's going on, then you can just kill the simulation. So how is it implemented? Let me just unfold it step by step. So at the beginning, we have MGPUSim, and the user provides a hardware configuration that is to be simulated. Then we provide this Akita library. Then if we provide a Go interface between the Akita RTM and the simulator. Now, because there's an interface, then if you don't use MGPUSim, if you want to write something, another simulator that still use Akita framework, yes, you can just call this API and automatically communicate with Akita RTM. It's actually a very simple API. Then when we start a when we start a simulation, we actually start two threads. Other than the simulation, regular simulation thread, we start a server thread. So we turn every simulation into a server that can spawn a website. Then we can monitor the execution on the website. Now, if a user wants to check what's going on with the simulation, then they use something called Akita RTM frontend, which is a web-based tool. Now they can, in this web-based tool, they can send a request. They can manipulate some DOM element so that they can send a request to the serialization to the server thread. The server thread will query the data from the simulator thread. So for example, we want to check some component status. Then we can get the data, then use a serialization library and send it to the Akita RTM frontend so user can monitor what is going on. And what does the interface look like? And if we have time, we can demonstrate live with you how these things work. But let me show you on slides first. This is what Akita RTM looks like. Now it's purely in the browser. So first thing is we have a resource monitoring. Now we can see how much CPU resources is used and how much memory is used. In this case, 117% is slightly more than one core is used. Now mainly we use a serialized simulation, so that uses one core, but Go like garbage collection or Go's library may use another core a little bit. Now we have a bottleneck analysis, then which analyze which buffer is full. I can show you later. Now we have some simulator control. For example, we can pause the simulation, we can resume the simulation. If you don't want to kill it, we can just pause it so it won't occupy a lot of CPU resources. It only stays in the memory. Then on this side is the main simulation monitoring tool. It's a little bit similar to GDB, so that you can check every variable's value live in real time. So you can check pretty much every variable that is being simulated on this tool. Now on the right side, we have this simulator profiling tool. So it's pprof. It's basically pprof, but visualizing a different style. Then you can see in this case, the first one is sim.taking component.handle, which is basically the pretty much the entry function for every component that they are doing their logic. It's very reasonable and it takes a lot of time. That is ranked to the top. Then, so you think this feature is really a small feature, right? You can do it with GDB, with pprof, no problem. Yes, you can do with pprof, but you know how much it gives us this convenience so that it can enhance this tool. Because every time I need to go online to check what is the pprof command, then because I need to go online to check the pprof command and type it um, in the terminal, I am too lazy to do it. But with Akita RTM, it's just one click away. Then I'm much more likely to click on it. So I'm much more likely to monitor the simulation performance. That is actually a very useful tool so that every time we develop some new feature, we just, as a habit, we check the profiling and see if there's something weird happening. If there's something weird happening, that's something like TLB is taking 80% of execution time. We know there's something wrong. Now we optimize the performance before it's getting into a bigger problem that we don't know how to solve it. Now at the bottom we have some visualization. So if you can click on a flag on the DRAM on this screen, then we can monitor some variables and see how it changes over time. At the bottom we have a progress bar monitoring. So user can define what progress bar they are monitoring. They can call APIs to define progress bars. So in this case, we can know, say, in this case, is the number of blocks that is being completed execution. For example, 15,000 blocks are completed. So we know if the with the simulation is making progress or not. So this provides a really, really useful tool for us to detect honing problems before it really causes problem. So we try to use this visualization tool to solve many problems, and even just in during our meeting, like meeting with students, with meeting with collaborators, we just use this tool and run some live simulation and monitor how some value changes. Then we can immediately get some insights without waiting until the next week's meeting. Okay, that's Akita RTM. Let me finish the Dyson part, then we can go with some live demo. Okay, so Dyson is another tool that we call it a post simulation visualization tool. So it's Akita RTM is during simulation visualization monitoring tool. So while the simulation is running, we want to detect some problem, understanding some, getting some insights. And Dyson is another tool that we want to run after the simulation is completed. So once we have a trace, we can analyze and understand what exactly is happening. So what motivates us to do this work is basically we started with a demand survey. We surveyed with 37 participants, and most of them analyze computing system performance as part of their daily job or research. Then they a lot of them express their need that they need more tools to understand performance metrics, and they think visualization tools may be helpful for examining performance issues. And in your open-ended questions, like 56 of them, more than half, mentioned they use guessing to identify performance bottlenecks. You can just imagine if you're when you are analyzing performance bottlenecks, are you guessing? Very likely you are guessing for the first time, then you're looking for evidence. Now, it's a problem that you can find evidence or not. Sometimes you can find evidence, sometimes you just cannot find evidence, right? You may think, oh, this may be the reason. That if it makes sense, you may take it as this is correct. But we need more tools. Then we need visualization to help users to understand what's going on. So we start by creating a new data abstraction. So we want a very, very simple data type to be able to represent everything. Remember, Akita, Dyson is part of Akita. Akita is an engine that is generic. It's not a cache simulator and not a network on chip simulator. So we don't want to create a visualization tool that is specific for network on chip or cache. So we wanted one style of visualization that works for all the computer architecture components. So that's why we create a super simple generic data abstraction, a data type. So we record everything as a task. A task, like an instruction, can be a task, or a cache transaction can be a task. And we record the ID, we record a kind and what. For example, kind is an instruction, what is a particular add instruction. And we record a location where it happens, then the start time and the end time. Then we add one extra field that we think is really powerful. Then we add a parent ID. By converting by converting a list of tasks into a tree of tasks, we can build a whole execution tree. For example, if we're executing a verb here, then this verb may have multiple instructions. Then some instructions are memory access instructions. It may convert into a L1 cache task, L2 task, eventually goes to DRAM. It can help us understanding from the bottom to the top, the whole picture of what is going on with the simulation. So with this data structure, we created this visualization tool that is called Dyson. Then this is the core part of Dyson. As you can see, the visualization style is in general in this way. On the top side, we have this called, it's similar to the flame diagram. So we have a current task and a parent task. Now if we select one task as current task, then we show this task and its parent task. Then we show its all subtask in the next level, as shown below. So this is particularly a verb that is executed in a GPU. So you can see there are many instructions being executed. Some of them take really long time. The pink bar is running really long. There are a lot of other bars that just take really short time. Those are very likely ALU instructions. And at the bottom is the component view. We call it component view because we consider this part are all the tasks that are being executed in this particular component. And we show it in nested Gantt chart style. So the x-axis is the time and the y-axis just represent the parallelism. We just don't want to overlap them. So if there's another task, it just goes to the bottom. Then, so you can see all the tasks that are executing. So one particular question that we want to answer here is, say, why one task start at this time? Say, for example, there's a gap here, right? We just want to answer why there's a gap. Why this verb or this block cannot start at the earlier time. Those are the things that we want to answer. And Dyson can at least provide you with what this component is doing and can probably give you a hint saying if this component is busy doing something at this moment. Now, other than this detailed view that can show every component, now we have this overview panel that can show a lot of components at the same time so that you can compare some metrics. So each figure is a time series chart. Now on the x-axis is the execution time, and then on the y-axis is the some values. For example, here we have buffer pressure, right? Now consider buffer pressure. We don't record buffer values. We only record tasks. But there's a task hierarchy, right? So if one task happens, say, at L1 cache, then stop task happens at L2 cache. We consider the part that if it started in L1 cache, but the stop task is not started at L2 cache, we consider this task is in the buffer of the L2 cache. In this case, we can calculate the buffer pressure. So we really use a simple data structure to represent something that can be really complex and helpful for users to analyze what's going on. So we have multiple metrics here, but as you can see, some values, for example, here, this value is 1.2 E minus 2. So that shows the buffer pressure is below 1. It's a time averaged value. So if it's below 1, that suggests this component is not likely to be a bottleneck, right? So this really quickly concludes the Dyson part that shows you what you can do with Dyson. So let me give you a quick live demo and show what's going on. Let me see. I just need to check if you can see my terminal or not.
Yes, we can see.
Okay. Okay, that's good. So let me run some simulation. Okay, I always want to start a simulation with this tool called simulation called FIR. So let me zoom in a little bit so that I can see clearly. As you can see, before today's talk, I just prepared some um, examples so that I know I'm sure it's running. But pretty much like we care about the coding quality, so we care about every time if we want to demo something, it's always ready to demo. The main branch is rather stable that every time we can show something. So I run a simulation. I intentionally let me add an extra zero so that I can run sufficiently long time. Actually, let me run unified GPUs equals 1, 2, 3, 4. So I can just run this large simulation with 4 GPUs. Then, as you can see, we print monitoring simulation with this link, right? It's a localhost link. Now I can click on it. Let me rather than click, let me copy paste into my Safari browser. Okay, as you can see, this is the interface of Akita RTM, and it's a pure browser-based application. Do a quick refresh so that it can work better with the screen size. So at the bottom, you can quickly see there are 4 uh, circles, pie charts. Those are progress bars. If there are too many progress bars, we don't want to show 4 progress bars, take too much screen space. So those are progress. So as you can see here, those are the live execution time in the being simulated. Now let's quickly, the first thing I typically want to look at is this tool. It's called bottleneck analysis. Now if I click on it, what I can see here. Now I can see, okay, L1V TLB, this is a TLB, response pipeline buffer. Then size is 16, capacity is 16, and it's automatically refreshing, and it's always full, right? So that means, oh, TLB here, for some reason, is either going up or going down. There's something that very likely there's a performance bottleneck at this moment. Now, if this is something you're expecting, then your simulation is right. If you're expecting TLB shouldn't be a performance bottleneck, then you can wait for 5 minutes. This is probably just warm-up effect and wait for 5 minutes, 10 minutes. If it's still a performance bottleneck, something wrong with your implementation, just kill it, right? So a quick analysis of what's going on. Then we can also take a look at something more detailed. Then we can see, oh, these are all the components are being modeled, right? So for example, this MMU. So the MMU and driver in MGPUSim is on the CPU side. So they do not belong to any GPU. So we can check this one. Let's click on this button. It's called working translations. So look, it's interesting, right? The working sim translation is 0, so MMU is not busy at all. Then, oh, it's going up, it's 1. Okay, but it's for a very short time, it's 1. It's not busy at all. Now we can come here and look at L2 TLB and see if L2 TLB is busy or not. Then we can see the, for example, responding pipeline. Then there's a post pipeline buffer. Then look at number of element. Then for this element, well, okay, in this case it's also 0, right? So, but quickly, just you can keep doing this by monitoring something else. For example, I can monitoring this thing called RDMA. RDMA is is the network interface between one GPU and another GPU. Now we can click on say transaction from inside and transaction from outside. We can see, oh, the RDMA has transaction from inside that is 800, right? Transaction from outside is only 5. So what does this mean is means we try to send a lot, but we receive only a small number from another GPU. I know the reason is because the GPU to GPU communication is super slow, so that a lot of transactions are being queued in the RDMA. But with a really short time, like 5 minutes time, we know what is going on, right? So this is the power of Akita RTM. With a very short amount of time, we know we can get some insights, and probably we can just kill the simulation. Let me kill the simulation here. Then let's go back to Dyson. So I have collected a smaller simulation with traces. It's in a SQLite 3 file. Then it's already running. So let me start localhost 3001. It's here. So let me start from scratch. So this is Dyson. Then you can see this is a Dyson interface. As you can see, there are a lot of components here. This is a really short simulation, so it's not very interesting. But I can already show you something. So for example, if I care about L1 cache, I just L, L1 Vcache. Okay, if I care about L1 Vcache, you can type L1 Vcache and you can move this a little bit. So as you can see, if I'm manipulating one time axis, then every other component is also moving at the same time. So you can see L1 Vcache 0, L1 Vcache 1, 2, 3, and the shader array 1, shader array 2. So as you can see, you can make an easy comparison, see if they're doing similar work or they are doing different amount of work. It looks like they are doing a very pretty much the same amount of work. So let me zoom in a little bit to a small value. Okay, so we want to know what tasks are being executed at this moment. So we can click into this cache. Now we can immediately see, oh, those are all the tasks that are being executed in this L1 Vcache. Is it busy? I would say it's at most a little bit bursty, right? Because there are some tasks that arrive at around, but in between the L1 Vcache is idle. Then, so let me ask a question then. Why this one takes so long time? There's such a long gap between these two. And how we can examine that? We can click on this one. Then you can see if I click on that one becomes the current task. There's a subtask and there's a parent task. Now if I clicking on parent task, we can go back to trace. For example, here, it's an interesting point. This is address translator. In address translator, if you can hover on this is a request out translation request, right? You can immediately see how long time translation takes. And this is a memory read request, right? So by comparing a translation request and read request, we can immediately compare, say, oh, the translation request takes about 1/10 of the total memory access time. Then it's really up to you if it's meeting your expectation. But at least you know what exactly is happening cycle by cycle. Now we can keep going up until, yeah, at this point we finally reach the um, compute unit, which is the core of the GPU. Then you can see there are so many instructions are being executed, and there are memory instructions. Those are all memory instructions, right? The purple thing. Then the very tight small ones are VLU instructions, are floating point operations. So you can see the execution pattern is a phase between memory access, some calculation, memory access, some calculation. Now we immediately identify the problem, the phase, and see if there's like a memory bottleneck. Okay, so that concludes some live demo. So if you have question, feel free to provide just send a chat message, and then we can see it. We will try to answer the question. Let me go back to the slides. So we want to just going more generic, say what is human-centered research in computer architecture domain. Then how is different from something we typically call engineering effort. And then I guess many of you may have this experience, say, from the review, say you're doing something engineering effort. Then how we can make it more generic and more research values. So human-centered research method starts from human and ends with human. So at the beginning, we try to understand the humans or human developers' true needs. On the other side, we evaluate with human to see if our intervention or our tool is useful or not. Then there are several stages. For example, identifying problems. So, for example, hard to explain problem. Then every time your advisor asks you to explain something, then if you are bullshitting, then that's something you are struggling. Now, if you're struggling, we say, "Oh, I don't understand what's going on with my simulation." You can reflect your struggle or your problem through a human-computer interaction lens. Say, "Oh, this is a human-computer interaction problem. This is a black box problem. Can we open the black box using some tools that can boost the productivity of the community, not only for us, right? But we are the user. So we know the problem, then we can identify the problem and solve these problems. Now we can evaluate the needs. So we can do surveys or interviews to understand if really the users have these needs or not. Then we can design prototypes, then iterate with users to ensure their needs are addressed. Then we can implement new tools and just consider the real world use cases with user barriers. For example, one particular thing that I keep saying why I think Akita and Dyson is so easy to use is because you don't really need to install any dependency. You just you if you have the Go environment, then you can run it. You can run it on Mac, on Windows, on Linux environment. You don't really have to have a certain GCC version, Linux version. It pretty much always work. Then eventually we want to evaluate the effectiveness with either qualitative method or quantitative evaluation method with users. Then another thing I want to talk is why this is not an engineer effort, why this is research. It's in the human computer interaction domain. There's a concept called research through domain. For example, if I want to ask you this research question, I want you to do a research to solve this problem. How to design a tool that can help users explain simulation results? Or what is user perception on super complex computer architecture designs? Right? In these type of cases, these questions, research questions, are super hard to answer with just one paper. What we can do, we can break it down into tangible step by step, right? We start by design something. We design something and see if it works. So we start by some design. Now after some design, we evaluate with users and using this process, we understand if users understand it or not. We can get some um, lessons learned and summarize and publish into a paper so others can learn from our experience. Now, after research, we had some guidance, we know some feedback. Now we can come back to design the next iteration of our tool and to make our tool better. Then we call this research for design process. Now, once we have this design, we can go back to research and we repeat this research through design process. And we enhance our research and summarize some better lessons. Then through these iterative designs, eventually we can create something, we can create artifacts, and we call this infrastructuring process. Now we create an infrastructure for the whole research community, which is very valuable for the research community. Then, okay, so let me summarize some takeaways. These are highly this is my personal opinion, and you can either agree with it or not agree with it. I think system or computer architecture research is much more broader than you may think. Then many problems are human-computer interaction problems. Even let's say, how easy it is to write an assembly, right? What is the mental burden to write an assembly code? What is the mental burden to write a code, C code or CUDA code? Those are HCI problems, right? So why Jupyter Notebook is so successful? It's not some technology advancement. It's some user experience advancement. And research in combining system research with HCI can be a new direction. For example, Akita RTM is the first of its kind paper that is published in Micro that we perform a evaluation using interview-based evaluation method. And I'm really happy to see that our community can accept this type of research and that they can accept it into Micro. Okay, so that concludes my talk today, and hopefully it's helpful for you.
Great, thank you so much. It is such an insightful talk with live demo. And we have some people over here. Any questions from the audience? You can ask over the live chat. So while waiting for the questions, I have some questions. So I didn't even imagine that the architecture simulator can be this much colorful. Thanks so much. And then these tools will be very useful, like to early stop any simulation, and also easy to do the analysis, right? You already showed this kind of a graphical view of all these kind of statistics, right? So then,
So now you know why your student like to use MGPUSim, right?
yeah, exactly. My students are big fan of your tools, right? So that's why I understand that my students always told me that it is really, really easy to use and then very useful. But one question is, what is the overhead of the real-time monitoring? Like some industry tools like MVProf is also useful, but it delays some of the executions, or even on the real systems. So do we need to concern about some delay, even though we know this value of graphical analysis?
Okay, so what's the overhead for the monitoring tool and the
Right.
visualization tool? Monitoring
Yes.
tool, the overhead is super slow. Is sorry, it's not super slow. It's super small. Um,
Mm,
Almost no overhead because we have like it's all on-demand serialization. Then if you 99% of time I don't even open it, right? If I don't open it, there's no overhead. Then, but if I open it when I'm running a lot of simulations, I may just randomly check one of them and see if it's matching my expectation. In this case, only if you click one component, it will serialize one component, right? It's only you click that moment. It's a quick serialization that happens, and um, it's actually because of we want to reduce the overhead. It's a little bit risky that there's some race conditions can even happen because there's one thread is running simulation, the other thread is running serialization. So probably some fields may be like in previous time frame, some fields may be in the next time frame. But because we want to refresh it again and again, so we don't really care about that the consistency that much. So pretty much in our experiment that we published in a paper, the overhead is negligible. But Dyson's overhead is not negligible. Previously, we're using MySQL. Sorry, previously we're using MySQL. Then the overhead is about 10 times slower. It's much, much slower. And not only this, um, the the hard drive is rather a limitation. Sometimes, like
mm,
we're recording cycle by cycle details. There's hundreds of components, right?
mm,
So it's really slow. Then, like a few seconds of execution can generate a few gigabytes of data. So we rarely run very long simulation to take traces. But there's one interesting project that's currently going on is combining Akida RTM with Dyson. Is we provide a button in Akida RTM. Then if we find something interesting and we want to analyze later, we can click on start tracing and just wait for like a minute, 2 minutes, then click on stop tracing. Then only a small part of trace is collected. Then we can analyze it right after,
mm.
even without waiting for the simulation is completed.
I
So that is
see.
a project that's going on, but probably gonna take some time to finish.
That makes sense. Seems like there are a few rooms to research, right? So this is a research for tools for the people. Okay, that's great. So I believe this is a really like a rare simulation work that think about the human and simulator interaction. What do you think your unique method means to the community, and do you think others can follow?
Um, yeah, I think my unique point is almost never people combine these two domains together. I can almost never, probably there are a few, but very few researchers working in the interaction between human computer interaction and computer architecture. So I think tooling are actually very important for our community. And I'm really glad to see that, say, 10 years ago, it's probably really hard to publish a simulator paper in Iskal Micro. And then today, it's not that hard. And then our community is accepting this type of effort to building infrastructures and to accelerate our innovation. So I think this method can, like others can try to follow this method that can develop these tools. And um, one very practical concern is just prevent others saying it's an engineering effort, right? So we always work on this type of tools with a research question or understanding something, understanding how human can understand computer architecture or how human can work together. So I don't know if you notice there's a Dyson bot button. This in the Dyson. Then it's a LLM tool that can interpret what is going on in the visualization tool. So it's totally
That
not
sounds
ready to be
interesting.
used. Yeah, it's totally not ready to be used, but I think this is gonna be a really interesting contribution. And by the way, this we're going to present this work in the CAMS, the Computer Architecture Modeling and Simulation workshop. So
Mm,
it's a very early stage prototype as at this stage, and a lot of work to continue working. But it just show our direction, right? So we have like a research question, like how human LLM and visualization can work together. This is or something that we want to explore. Then we design this tool to be both useful and in terms of practicality and also useful in terms of threat theory understanding, right? Research through design. There must be a research question that we want to answer, and there must be something that we want to implement. So iteratively that we get better lessons learned and better design. And eventually, if we have a good repository of software infrastructure, then hopefully others can use our tool.
mm. There's one question from the live chat. So will this monitor tool be portable into other simulator or how this idea could be expanded?
Okay, so how this tool can be used in other simulator. Um, so let me have two fold of this answer. The first side is um, it's a web-based tool, right? So web-based tool has a clearly defined HTTP API. It's all HTTP API. There's no WebSocket. There's no magic there. So if user click on something, then we send an API, say, I request this detail of this particular component. I send you the component name, you just provide me the component name. If your tool can provide me the component name, then the details of every field of this component, I can show it there. And then you can use it as a tool. So we have this HTTP API defined. It's an open source tool, so you can check the API. Um, so in theory, yes, you can support any simulators, Gen 5 to and connect with Akita RTM and even Dyson, no problem. On second side is consider how hard this will be if you implement it with C++, right? So even just creating a server with C++, HTTP server, well, there are some libraries, but just using libraries is problematic. It's not impossible. It just requires you more work than Go. Now, if I work on Go, I find a library. Now I just write one line I want to use in this library. Now I can use it, no problem. And it automatically works in Linux and Linux and Mac, any platform. So this is really something that every time I get a review, they say, "Oh, you're using Go," but our community is not using Go. We have spent so much effort in C++ or C. I'm just thinking, well, probably it's time that we can shift to some easier to use languages, right? Easier to develop. We have LM today. Like automatically converting from one language to another is not super hard. So probably it's time that we should I don't say Go is the ultimate solution, but just gradually try some different languages, try some different solutions. Maybe something that can, in 10 years, 20 years time, can accelerate the productivity of our community.
That's good. So speaking of that, we should value all these efforts from those who develop these well-known simulators. We owe them a lot. So then, speaking of that, like, do you feel that you get sufficient incentive for maintaining these research infrastructures for the community? Any interesting stories or challenges to share?
Yeah, as I mentioned, like 10 years ago, it's probably really hard to publish into ISCA, right? There are many people say, well, you can publish to ISWC, but you know
Mm,
the situation. Then
right.
if you are looking for a faculty job, ISWC is not that valuable as a ISCA, then just very unfortunate to say that. Then um, 10 years ago, when I first started this type of projects, I find it, I don't know how to publish. I don't know how to frame it into a good story and publish to a good conference. Um, by that time, I was really concerned about the incentive. Should I work on simulator infrastructures? And later on, especially starting from 2018 to 2019, I pretty much every year I can see some infrastructure papers in every top tier conferences. There's probably even a whole session that's on simulators. And so I can see that our community is getting a lot of like attention to this domain. So then gradually I feel it's actually not that hard to publish this paper. Now, of course, I hear people say, "Oh, I write 800 lines, 900 lines of code, I can publish two paper." Then if you're working on infrastructure, it's not the case. You write 10,000 lines. No, 10,000 lines is impossible. 50,000 lines, probably that's one simulator paper that you can get published. So the publication cycle is much longer. Then you still need to find story, and it's not easy, but eventually you can get your work published, and I'm very happy that our community accepting it. And another thing is typically this type of tool, if you really maintain it, you keep having it developed, the citation is rather high. So that's something that I feel I get sufficient incentive. And also, if you become a professor or PI, you will notice that there are infrastructure fundings. Those are infrastructure fundings by NSF that are really encouraging you to do solid work. You don't have to worry too much about publication. You can just spend time and even hire someone professional, someone full-time developers to work on your infrastructure. So I feel that because I have a unique simulator infrastructure that have unique advantages in being a PI and leading a research group. And on one side, I have infrastructure to do research. On the other side, infrastructure itself can get research fundings. So overall, I find I'm really like I get sufficient incentive to support me keep working on it. And at least it's really fun to develop these tools, right? Also, um I I always say that if I develop a GPU architecture, I don't know if AMD or NVIDIA will take it or not. How long time that will put in production. But if I work on simulators, I put it on GitHub. Probably in a month, someone will start to use it. Then I see on GitHub like many users that I even don't know just contact me, and they are using the most recent features of MGPUSim. So I get really happy that I can see immediate reward from the community.
That's great, right? So then, what do you think? Like you said, it takes lots of time to develop these infrastructures. Then, um, and you did a lot of the pioneer work already. But what do you think is your vision for these projects, like in next 10 years or so?
Okay, I have a lot of visions. So um, there are many things that I can do. Like so, I can tell you at least pretty much Akita and MGPUSim, if you check the repository, it's very likely to have daily update. It's either from my PhD student or undergraduate students from Villamary or even contributors from all over the world that I don't even know them. So it's a iterative improving tool. So right now it's Akita V4. We're developing Akita V5 to add some serialization feature that is a must for simulator, but we don't support it yet. So those are some short-term goals. Just keep iterating, adding new features. So in general, I want to go with two directions. I think that's why I'm saying I'm not really competing with Gen 5 or GPGPSim. That I, from my understanding, they do not care about this tool. They mainly care about fidelity and the wide variety of hardware that they can support. But I really care about two things. The first is credibility, right? So I always have this question that are simulators accurate enough? And when we report average errors, like 20%, what does it mean? 20% of error. Then if I run some simulation, does that mean if I put it in production, it's still less than 20% of error, right? It doesn't really mean that. How we can understand it? Then simulators have a lot of like free rooms, like moving parts that can have some problems. How we can know that this we can trust this type of uh, simulation results, right? When we talk about trust, the subject is always human. Then it's a human-computer interaction problems. So how can we trust the simulation result, and how we can provide the just sufficient evidence that our simulator is trustworthy. Can you say, oh, MGPUSim, I know is simulating R9 Nano GPUs 10 years ago, 2015 architecture. If one paper say I converted MGPUSim, I modified the configuration to model MI100 GPU or MI300 GPU, to what degree you can trust this result, then how we can provide the least amount of information to give you this trust. So that's the first problem. Then the second side of problem is how we can make it understandable, still understandable. For example, in Akita, in Dyson, we still have these problems. The every user, even myself, have this problem. That I find, oh, this task starts so late, or this task takes so long to execute. That is also all the subtasks are completed, but this current task is not completing. How we can answer this question? I don't know how to answer this question. There are many situations that, or sometimes I can answer this question because I wrote a source code. But if someone who didn't read the source code cannot really answer this question, then how we can make a rather entry level, like with a few years training experience, can answer most of the questions, can analyze performance. So those are my vision. So in probably 5 or 10 years, and that's something I really want to do, really achieve next.
Great. So yeah, so we look forward to new features of these tools and new tools to make our life easier. So yeah, we want to keep getting these new efforts for the tools from the community. This is really important. And also, you're gonna host another the workshop about the simulators, right? CAMS?
Yeah, so the CAMS, the computer architecture modeling and simulation workshop will happen right at the weekend right before micro, right? So it will be in Korea, and so I will not be there, but I will join remotely, and our co-chair Trevor Carlson will be there to chair the sessions.
Hey, sounds good. So
Yeah.
please try to attend the workshop if you are going to attend the work micro. Okay. So then, okay, let's wrap it up over here. So then, thank you all for staying with us. And then we're going to continue this effort. If you have anyone in mind to learn from or topic to learn, please send messages to our TCR LinkedIn or X account. And see you at our next talk soon.